喂喂，可以听到吗？喂，
哎，可以，可以，可以。
哎，好，好，我这网络没问题哈。
好，
哎，是
可以，
如林吗？
是是是是是，可以，可
哎，
以。
好，谢谢啊，谢谢，谢谢，谢谢。好，我在这等一会儿。
Hello.
Hello, Stephanie. Hi, long time no see.
That's right. How are you?
Yeah, good, good. How are you?
Good. Yeah, a bit tired. It's
Yeah.
midnight here, so I'm just like just trying
Oh,
to stay awake.
oh, okay, okay. I see. We have 3 minutes to go.
Oh yeah, yep, that's good. Yeah. So is there anything I need to consider with regards to the presentation or
Uh-huh. Okay. So your talk will be 40 to 45 minutes, and we have maybe 2 or 3 questions, or 1 or 2 questions from the audience or from me. We
Mhm.
can discuss a little bit about your talk.
Sounds good.
Mhm. Oh, I think the second speaker, Ziqi, is also here. Hi, Ziqi.
Hi. Yeah, sorry, it's
Hi.
very early in the morning. I'm in
Yeah,
Boston, so
it's
it's
your early morning, and Stephanie's late night.
yeah. Looking forward to your talk, Stephanie.
Um, I'm actually also looking forward, but I might watch your talk later on because I'm not really sure if I can stay awake that long because we
Hmm.
also have like a staff meeting tomorrow morning. So yeah, I apologize if I can't stay.
Mhm.
But I yeah, I
That
watched a
doesn't
couple of
matter.
the
Hmm.
other presentations already, so on YouTube, so that's actually quite good.
Good. Yes.
Thanks.
Okay, I think we can start. Okay. So, hello everyone. Welcome to the AsiaGraphics webinar session 29. I'm Miao Wang from Beihang University. And today it's my honor to have very excellent speakers, Professor Stephanie Zoman from the University of Otago, New Zealand, and Professor Ziqi Wang from EPFL. So we have two excellent talks about XR in sports and computational assemblies. So the first talk will be given by Professor Stephanie Zoman. Stephanie Zoman is an associate professor in the School of Computing at the University of Otago in New Zealand. She's co-leading the Visual Computing Otago Research Group. Before starting at Otago in 2016, she worked as a senior developer at Animation Research Company Limited on extended reality visualization, computer graphics, video processing, and computer vision-based tracking technology for sports broadcasting. She also works for Daimler and Graz University of Technology. Her main research is in the field of visual computing and human-computer interaction. Her research focus is on the extended reality for sports and media, studio-aided realization techniques for AR, and the novel methods for capturing contents for immersive experiences. Stephanie serves on the editorial boards of TVCG and Computers and Graphics. She was also a program chair at actually ISMA in 2019 in Beijing and 2019 as well for actually VR 2024. The talk title is XR in Sports, Enhancing Broadcasting, Spectating, and Training Through Immersive Technology. So, Professor Stephanie Zoman, the time is yours.
Awesome. Thank you so much for the very nice introduction. And yeah, I still remember visiting you in Beijing. So this was a great time when I was program chair for IEEE Isma. So it was really nice. So it's great to join now online. And I hope this is now working. Let me have a look. Okay, so I hope you can see my screen. If not, please jump in. So yeah, so what I will do today is I will have a
Sorry, I can't see your slides.
oh,
I
you
can't
can't
see
see
your
my slide.
slides.
Oh,
Oh, now
okay.
we can. Yes, now it's okay. Yeah.
Okay, give me a
Okay, go
second.
ahead, please. Mhm.
Is it still good?
Yes, it's good. It's good.
Okay, that's great. Yeah, it's always a bit of a hassle with with Zoom and the screen sharing. So what I will talk about today is XR in sports. And in particular, I want to talk about how we can basically enhance broadcasting, but also live spectating and training by using immersive technology. And yeah, I already had like a very nice introduction. Just a couple of more words here from my side. So basically, I'm based in New Zealand at the University of Otago, and my main background is in visual computing. So I'm very much interested in everything which is related to graphics, computer vision, but also really trying to bring this kind of human component into my research. And in particular, I'm basically coming from a background from augmented reality and mixed reality, virtual reality. I started my early research with projection technology, so this is basically where I'm coming from. But I also have like a very large interest in sports and entertainment and how we can use immersive technology for these kind of areas. And on the other hand, I'm also very interested in industrial applications. And this basically comes from my earlier research when I was working for Daimler Research. And also during my PhD, I was doing like lots of research in the area of civil engineering. So how can we visualize, for instance, infrastructure that is under the ground by using, for instance, an augmented reality interface. So, and on the right-hand side here, you can see a couple of the work that I was doing before joining the University of Otago. So at the University of Otago, I'm co-leading the visual computing group. And here we have lots of students that are really interested in everything that is related to augmented reality, virtual reality, and graphics and computer vision research. So and this is basically part of the School of Computing. This is like a newly formed school here in Otago. In the past, we were basically two departments, information science and computer science. And now we are the School of Computing. And I'm basically working in this kind of area on visual computing for sports and media. So the first thing I would like to start with here is actually just briefly talking about what is it actually when we're talking about XR, because there are a lot of different definitions in the room. And for those of you who attended the ISMA conference that was happening a couple of weeks ago, there was a huge panel just discussing the different terms here, and basically people interpret this as, for instance, extended reality or X reality or cross reality. So I just want to briefly go in here to just have a bit of a clear definition so that we know what we're talking about. And when I was looking into the previous talks in this seminar series, I noticed that there was not too much in the area of augmented reality and virtual reality. So I think it's maybe still, good to just go over this. So if you're looking into this kind of classical or traditional definition by Milgram, where we have the mixed reality continuum or the virtual reality continuum. We basically start here on the left-hand side with the real environment, which is basically everything that surrounds us. So just our actual environment. And then we basically move along the continuum and we insert more and more digital content. And this travel, we basically then come along the augmented reality area where we have still our actual environment around us, but we enhance this with digital content. So for instance, in this example here, you might have some kind of instructions where to go. You might get some information about sites in your area. And then we basically move further along the continuum. And here then we have augmented virtual reality, which is a virtual environment that has still real information embedded. So for instance, you could imagine this to be, for instance, like videos of a real environment. So you really just try to integrate like real data into a virtual environment. And then once you're replacing everything, like all the real environment with completely virtual content, you're basically in this virtual reality, virtual environment area. And then what you can see here, we basically have this kind of definition where we talk about mixed reality when we're going from real to virtual. And also people often define XR or cross reality, extended reality as the whole area of augmented reality to virtual reality. So that's basically where I'm very much interested in, and I'm basically having like most of my research in this area. So just a couple of examples here, and that's basically from our very nice campus here in Otago. An example for augmented reality would, for instance, be we have like a historic photograph, and now we are integrating this kind of 3D representation of the historic photograph on top of the view of the real environment. So we basically just display this on top, and this allows us, for instance, to explore a location and look back into the past. So that's basically like a use case that we explored here. And then people can basically, walk around on our campus and just see how the buildings were looking in the past and get this kind of view back in time. And then in contrast, if we are, talking about virtual environments, we really, have like a completely virtual representation of the environment. In this case, we have a virtual representation of our campus, and then the user can actually just, navigate through this environment, and they might just look at this in a virtuality headset, so they can't really see anything that is actually there. So they wouldn't be on the campus, but they would basically be based maybe some like a different location, and they can still explore the virtual environment there. So that's basically how we're traveling along the reality-virtuality continuum. So the question is now, why do we actually need to combine XR and sports? So why could this be a good idea? And from my viewpoint, this basically was for me inspired by my work that I was doing for a local company, Animation Research Limited, here in Dunedin. So when I was moving to New Zealand, which is now roughly 11 years ago, I started to work for this company, and they basically do like lots of the graphics for all types of different sports. So they are really big in the America's Cup. So for instance, like sailing, they do like lots of the golf tournaments, and are really big in cricket and cricket visualization, cricket broadcasting. So I really work on a lot of really interesting sports and do like the sport broadcasting and sports graphics. And so this basically all broadcasting. So like lots of the processing would actually happen in a post-production step, but with like a very fast turnover. And when I was working for them, I was basically working in one project which was looking into how can we visualize snowboarders and also skiers that are going down really steep mountains, which is basically really hard to follow live. Like, if you're standing there, you're a spectator, you maybe just want to, watch the slopes. It's really hard to actually see where the riders are going down the mountain. So what we were doing back then was then looking into equipping the riders with GPS sensors, and then basically using tracked helicopter footage, and then visualizing the GPS tracks on top, which basically also allowed us to integrate lots of different statistics like speeds and also how steep the angles were, what kind of tracks they were choosing, and also having them basically in like some kind of side-by-side visualization. So for me, this was really like this kind of whole topic around how can we enrich sport broadcasting. So like if we're looking back in the past where you would maybe just like watch like a football game. Back in the days, there was not so much additional graphics, and I think like just if you look into like the last years, what happened in terms of the sports technology and sensors, and also really high performance computing, we really get a very highly enriched experience also for remote spectators, where we can basically access lots of additional graphics and statistics, and that can be quite helpful also for just making the the experience and the watching more exciting. So I was back then also working on, for instance, cricket ball tracking. So how can we track like a ball and then visualize this in a 3D flight path, and we basically also looked into just visualizing this in like different types of arcs and visualizations there, which can be quite helpful. So that's just like an example for where this was just demonstrated with some kids during like a tech week here in Dunedin, where you can basically just track the ball and visualize this directly in a 3D representation to just get a bit of a better understanding how the actual flight paths of the balls were. So at the end, you basically just end up with this kind of 3D representation, and you could basically compare the different flight paths here. So that's basically all broadcast, and has like a big focus on broadcasting technology, but also I thought this has actually like a really huge potential also for enriching live sport activities. So, for instance, if you're looking into sports spectating, like going to a match, and you sit down in the audience, often there's not a lot of additional information that you can access. You might take out your phone and you can access box score data, for instance, but it's certainly not the same what you would expect from broadcasting. So that's an example from our local stadium here, a rugby game, and this is basically like a like a standard view of a spectator in the stadium. So maybe you have like a big screen where you can access like replays and stuff like this, but you basically see what you see, and there's no additional information available for your own perspective. But also for sports training, like basically, if you're looking into how a lot of people nowadays do, for instance, like sport exercises, but also training, lots of people nowadays actually go to the video training. So, for instance, like using, for instance, YouTube for instructional videos, but also if you're looking into what's happening in a and gyms, often you have like you pre-captured videos, and then you can actually access these kind of videos from remote, so for instance from home, and then you can just follow the instructions to get your training session. And one of the challenges here is that you only get like one pre-captured perspective. It's not really aligned with your own body, so it's quite often challenging to follow the instructions, because you also have to do this kind of additional step where you have to map from a 2D space onto your own body, and just making this kind of connection. So we with our team here, we basically looked into additional options where we can actually use augmented reality to display and integrate sport instructions directly into the field of view of the user. So basically, instead of watching a 2D video, you would just get the instructions replayed, for instance, by an avatar, and then you have like the freedom to move around and just like, select like a position that is really suitable for yourself. To just follow what are the instructions by the teacher or by the instructor. And so from my point of view, there are actually like lots of potential in this area, because you can actually enhance the sports spectating, but also the sports training with similar technology that is already used in broadcasting. But of course, with the technology that is used in broadcasting, there's like lots of hardware, expensive equipment often used. So we can basically achieve like a really nice integration of the digital content into the broadcast footage, which might not be the case for the AR user or the extended reality user on site, because they often just rely on off-the-shelf hardware. So this basically brings us to the challenges that we are basically trying to address here with our team in Otago. So we mostly focus on what are suitable hardware solutions, but then also what are the challenges that we have to tackle in terms of the localization and tracking. So how do we figure out where is a user located? For instance, if you're talking about the stadium and a stadium live performance or like stadium live event, where are they seated and in which direction are they looking? But then also like aspects around visualization techniques. So how can we basically integrate digital content without overwhelming the user? And then also data creation and also data set creation is a huge topic for us, because if you want to test these kind of methods and developed algorithms, you actually need to have like really good data sets to reflect a highly challenging environment. And then the last point is actually user studies, which is also a challenge, as they are not, it's not sufficient to just run lab studies for these kind of use cases, because you actually need to go out into the field or into a stadium, into a gym to really get actual feedback from actual users here. Okay. So the first topic is basically the different prototypes, and here we looked into different possibilities or options, because the first prototype that we used was actually like a mobile phone prototype, because this is what everyone has. So it's quite easy to deploy an augmented reality app and then just using this directly out of the pocket. Challenges around this were that actually for the users, it's not really feasible to hold a phone all the time. So when we were running our first user studies here, we actually really ran into this kind of problem of hand fatigue, and it turned out that having like a mobile phone app for having like a on-site spectating AI application is more suitable if you only take this out from time to time to have like a to access information on demand. We also looked into different HMD prototypes. So for instance, here we were using the HoloLens back then. So that's a couple of years ago. And basically, the advantage in this case was that we just have like the full flexibility where the user can just really move around. They don't have to take the phones out, but it's still like a bulky device. So then for the AI training on the AI coaching project, we then also switched over to the Quest 3 here, and certainly the first feedback that we got here was that we just compared this, for instance, to like mobile phone prototypes. This would not be suitable. Like if you just use like a mobile phone, you can't really perform like all the actions and follow the instructions, because you need to have like the full body movements. So for this AI training, we basically then looked into using a Quest 3, or also we worked with the spectacles from Snapchat, which is like a very nice lightweight option to actually integrate this into a training workflow. So this basically also brought us to the challenges around localization and the tracking problems, because if you're looking into what we actually want to do, we need to know where the user or the spectator, and each of the spectators is located within a really large environment. So like, if you're looking into like a stadium, for instance, but even a gym, it can actually be a quite big environment. And then we often deal with users that are just seated. They don't really move around a lot, which is very different to the standard use cases that we have for augmented reality users that are often just exploring like a smaller space and accessing information about, for instance, like a living room, placing some furniture. In this case, for the stadium, you really have to cover like a very huge area, which is certainly a big challenge for the for any localization and tracking algorithms. And in particular, because these kind of environments are also dynamic, so that it's to the challenges here. And so this just like showing like an example for like a typical spectator perspective. So like, they don't really move around a lot. They're seated often, and they're just turning their head. So it's really also challenging for like SLAM-based algorithms. So when I was working for my PhD, which is like a couple of years ago, back then I was doing lots of outdoor augmented reality and basically looking into outdoor augmented reality for civil engineering. And back then we basically had like a really nice, robust way of localizing an augmented reality user in a large scale environment, for instance, in a construction site. So what we were doing back then was we captured like lots of photographs from the environment. Then we did a 3D reconstruction to create a point cloud and also post data for each view. And then basically you just go in with each new perspective where the user is starting their AR experience. You send an image to your localization algorithm, and this gives you some kind of post data back. The environment is mostly static, so it's actually quite robust in this kind of case. So and there are a couple of solutions where you can really use this in like large environments, and a couple of them were also like presented at the ISMA in 2012. So, but the problem is now, if we are looking into using similar algorithms in a sports environment, so for instance in a stadium, we have these kind of really highly dynamic environments. So this means we have lots of people moving around. So we have like all the players, they're doing something, but then also the environment itself changes quite a lot. So if you just look into all the spectators that are sitting on the different ranks there, they were not there when you might have constructed your 3D model for just preparing this venue. So the environment is really changing a lot, and you can't really prepare for these kind of changes in a way that these traditional algorithms would actually be able to handle this. So we tried this initially because we thought, this was working quite well, in the past. But like for the dynamic environments, it was actually not really working too well. So this basically brought us to moving us away from the traditional computer vision algorithms and really looking into machine learning based approaches, because they are more robust in the terms of handling these kind of changes over time. And one approach, which is called ESAC, or expert sample consensus, applied to camera relocalization by Prachman and al, was really robust. So we basically back then ran like lots of experiments in like different levels of crowdedness in a stadium, and really tried which kind of state-of-the-art algorithm is really robust in terms of handling these kind of challenging dynamic environments. And for our setup, we ended up with ESAC. So that's a short version for this algorithm. And what we then did was we integrated this into our augmented reality app, and then also used this on site for our on-site camera localization. So we combined this basically. Then what's happening is that you have to create a 3D reconstruction of the environments of the stadium. So you prepare the stadium by capturing like 300 or 1,000 photographs. And you can see this in the middle here in our localization server. We really have this kind of pattern where we just try to capture like lots of different perspectives of the stadium, and then we train the expert network. So you basically run structure for motion, and you feed this into the expert network, and then the expert network is actually able to compensate for like all these kind of uncertainties that you have from the dynamics that are happening in the environment, because it's always trying to find a consensus or like a really good estimate of the pose of the position and orientation of the mobile phone user. So we integrate this into our AR system. So we basically have like a mobile phone app, and then basically we can capture photograph, send this to our localization server, and a pose data is then coming back to the mobile device, and we can then integrate this into our on-device tracking and visualize our augmented reality content. So we also looked into like different other state-of-the-art algorithms, and what we can basically see here on the bottom in the graph is that if we are running the different state-of-the-art algorithms in an empty environment, they actually perform quite similar. So there's not like a huge difference. We have a reprojection error here of a couple of pixels, and I think we are using like a 2K image resolution. So like, if you look into this, it's actually like a quite good result for all of the algorithms. But then once we are actually, adding more and more dynamics into the scene and to our data set. So for instance, with our semi-crowded data set, I think we captured this during like a training session. So there are a couple of more people in the stadium. You already see like the reprojection errors are going up. And then once we run the same algorithms on a fully filled stadium, like a crowded environment, all these kind of different all these kind of algorithms are actually performing quite differently. And what we basically found was that ESAC, either with using 4 expert networks or 10, is actually performing best for this kind of use case. So was actually quite helpful for us, because we then found a good implementation of a method that was robust enough to really handle these kind of challenges around having like a highly dynamic scene. But then what we get out of this is basically just a position and orientation of the spectator, but we don't really know, where are they moving, because we can't really, send like lots of images to the server and just wait for the response. We actually also want to have some kind of on-device tracking, which basically continuously tells us where the user is looking and just updating this on the fly. And the problem here is that if you're looking again into what the usual movements are, we can see that there's only like a very small baseline. And if you worked with SLAM algorithms before, often the requirements here are that you actually have to have like a wide baseline to have like a nice initialization of your algorithm, which is not the case for the use case that we are working here. And it's not only case for sports spectating, but also if you're looking into, for instance, like tourism, where people are basically, trying to access information about a location, maybe some sightseeing. Often they, just stay static in one position and then just move around their phone. It's not often the case that people are just, browsing while walking, because it's actually a bit too dangerous. So we really, run into this kind of problem of having a small baseline here, and in our work, we then addressed this and actually took this kind of disadvantage of having, like a small baseline into an advantage, because we noticed that often really users of AI applications, they are standing static, and then they just move around on a circle, because they often just move around their arm. And we then integrate this as a prior into our into our localization and tracking algorithm by basically just assuming that the user is moving along on a sphere. So and this basically allowed us to implement a spherical perspective 2-point algorithm because of this kind of prior where we know that the translation is always fixed, and we basically just move around on our sphere. So to say, we can basically reduce the amount of unknowns, and then we can actually compute good results in terms of post data by using a 2-point algorithm. In addition, also this also allowed us to implement a keyframe sphere. So if you're looking into traditional SAM algorithms, you often have a keyframe map that is basically unrestricted. So like the keyframes can be everywhere. But in our use case, where we basically assume that the user is always moving along on a sphere, we can actually reduce the space to just having keyframes along a sphere, which also then reduces the space that we have to sample and also to search for. We ran a couple of tests on this, and for the kind of use cases where we basically have like a static user that is trying to browse the environment, we actually got like a really good result compared to traditional algorithms like OrbSAM, and our split algorithm, the spherical algorithm, was actually performing quite robustly. But again, there's like one use case. Obviously, once the user is moving further away, there will also be some problems. But for our use cases, in particular for the stadium, this was actually working quite well. So we can basically now assume that we know where a spectator or a trainee is located. We know where they're looking at. This means we can actually now integrate digital information, and we can basically place the information so that it's suitable for their own perspective and their own view, and they can actually access like very personalized visualizations. So but this then basically brings us to the next challenge, because if we're looking into now adding digital information into environments that are already highly dynamic, they have like lots of information going on, there are events happening, activities. Maybe there's, on the other spectator side, there's also activity happening. So it's already like a very challenging environment, and it's already, prone to information clutter. And what we now want to do is we want to actually integrate more information. So there's certainly a risk of overloading the user with too much information, and also possibly occluding important events or activities that the user actually wants to see with additional content, which it shouldn't interrupt or interfere with the actual sports experience. So this basically just like just to visualize, if we just have too much going on, it could be just a bit of a challenge here. So in order to address this, we actually looked into situated visualization specific for sports. And in our case, we really try to now analyze what are the best surfaces in the 3D environment of the user. So for instance, the play field, but also like the other spectator stands, in order to integrate additional information. And in order to do this, we integrated scene understanding. So we, analyzed the 3D environment, like a 3D model of the event site, in our case, a stadium, but then also integrating scene understanding that was just coming from the live footage, and just analyzing like where's the grass, where are the other spectator stands, and integrating this into our visualization methods to just make sure that we only display the content where it's really suitable. And we also looked into what are the different types of information that we're actually can visualize. So for instance, there's like word reference data. So for instance, you might want to visualize the different scores, but basically supporting the user by already showing which team is playing on which side. But then also in addition, visualizing events and just providing some kind of explanations. There might be some live tracking data from the players coming through. There you also want to visualize additional information, and we basically just try to now analyze where's the best location for displaying this kind of content. We also looked into then combine this with more traditional visualizations that are actually coming from broadcasting. So we just have like a 2D screen, and then integrating this together with the situated visualizations that are actually integrated into the play field and are visualized on the field and on the players. And then also we looked into how can we visualize time and event-based data. So for instance, if you're now looking into having spatial information, where we often get like X and Y coordinates from a game, and then we can actually just visualize the events where they're actually happening on the field by basically just displaying them in the overlay. And in this case, it can be a bit easier for the user to understand where the event is happening. But then also we looked into how we can actually make use of the context of the user, because often people are not just like following the action on the field. Sometimes they are browsing around, and in other cases they might want to have additional information. And you can often analyze the movement behavior, so either by eye tracking data, but also just by following the movement of the headset if you're using like a headset, and then using this in terms of analyzing if they are more focused or if they're agnostic, and browsing for more information. And depending on this, we were then looking into integrating this into like a level of detail visualization to either show more or less information, and to make the experience more customized for each user. So for instance, in this case, this is showing our level of detail framework. And then depending on if they're focused, we basically then just change the level of detail and displayed more information. If they were not focused, there might be some kind of quizzes that are displayed just to keep them entertained and engaged with the sports experience, which is similar to what we know also from what's happening on mobile phones. Okay, so the one of the last topics here that I would like to discuss is also the challenge around dataset generation or capturing, and how to run experiments in these kind of challenging environments. So obviously we had to capture like lots and lots of data sets for creating our 3D environment, but also training our networks, and then also doing our testing. And we basically followed like a very good plan here in terms of capturing our data, but also making sure that lots of different devices that we used were aligned to each other, and this basically provided us really good reference data that we later on then used for our experiments. Then for the training use case, we were also looking into like different types of data set capturing. And here in particular, we were looking into an egocentric versus an exocentric data set capture, where we basically look into possibilities for capturing training data where the instructor is moving around a lot. So where we can't really follow them with like a camera, and basically by having this kind of attached setup with a 360 camera, we captured footage and used this then to extract a 3D avatar that was then used for visualization purposes. So we can basically see this here in different use cases. So we basically explored lots of different sports, from basketball, skateboarding, soccer, over to golf, and then basically looked into how well can we actually capture these kind of performances with an egocentric camera setup that is attached truly to the instructor versus an exocentric data capturing setup. So then after we captured all this kind of data, we also were interested into now actually exploring how users would work with this kind of prototypes and with the kind of implementations. And we started basically back then with a miniature lab version because that's was one of the first things that we actually wanted to try, and it's quite easy to set up. But then we also moved into doing actual field studies, which is obviously something that is more challenging because you have to bring the people into the stadium. You have to look into making the environments kind of replicable and in terms of avoiding unexpected events. So we basically ran these kind of experiments in a stadium, and then looked into different factors, how people would compare this to, for instance, a standard on-site experience versus broadcasting and our visualization techniques. I will not go into too much detail here, but there were actually like lots of different options that we implemented in terms of running on-site and off-site experiments to really make sure that we get this kind of human factor and human feedback into our research. So just one thing here, basically one of the additional experiences that we implemented was being like a VR experience where we can actually simulate an experience of being in a stadium by using 360 footage that was then enhanced with our AR visualization techniques. And this basically allowed us to also run in-lab studies by replicating a very realistic environment and experience. So just to conclude this, my talk, so I still believe there's like lots of potential for using immersive technology in XR for live sports. But as you can see, there are still technological and logistical challenges. So in particular, if you're looking into implementing something like this, going or preparing a venue for this, it's still like lots of work and still quite expensive to do this. And then also, if you're looking into doing this kind of research, there's like lots of challenges. There are lots of challenges in terms of testing and deployment. You might have only limited access to the test sites. And also, particular live event testing can be very challenging. And you also run into problems where you actually want to have like a proper work environment for your developers, but they also want to do some on-site testing. So how to deal with these kind of challenges. And so basically what we can do is we can use XR to create interactive, enriched live experiences. We can present data that is relevant to the user and their context, and we can basically support users in their understanding by displaying this kind of additional information. And that concludes my talk, and I'm happy to take questions.
Hi, yeah, thank you very much for the very excellent work. And you did a lot of systems and jobs. So perhaps I will start with my question. So you mentioned several challenges about the hardware, the tracking, mobilization, dataset, and so on. So may I know if you have finished a lot of systems across different sports types? So are there any modules or methods can be reused across sports, for example, from the football to the basketball to the baseball? So may I know how much work do you need to to deploy the systems? And are there any modules that can be reused, and how you solve the problems?
It's a very, very good question. I mean, like everything that we build is it's more like a research platform, but we actually try to integrate or be flexible in terms of what kind of sports we are supporting. So we are mostly focusing on like the team sports, in particular for the spectating use case. So this means what we were just trying to do was when we developed our system, our platform, and I didn't go into the much detail there, but we actually have like modules where we can access like different sports databases, and basically like as long as the data has some kind of locations like X and Y coordinates, we can easily just convert this into like a stadium representation. But I think like one of the big challenges is to actually like expand this because like you can prepare like one stadium, but it takes like maybe 1 or 2 days to actually like completely capture this, train the networks, just making sure that everything works, and you have to like do your test runs. So it's actually like lots of hours that go into just preparing one venue. And I think that's basically one of the big challenges there. Like it's very, very specialized for a venue. And you can do it in different places, but it just takes time to just train the data, capture the data and everything.
Yeah. So my following question is, you mentioned the several, the networks, for example, the expert network, the CNS, the segmentation networks. So, do you think the large language model or the multimodal large models can be used to enhance your current solutions or systems or methods? And how, there is also, the spatial computing and spatial intelligence. So I think it's a very, your work is very excellent that we can go towards the spatial intelligence. So how do you think the LLMs? Yeah.
Yeah, and I think it's a very good question, because I think like that this space just developed so quickly over the last couple of years. And I think when we started, we basically so when we started with this project, we were still looking into a more traditional computer vision method. So because there was not so much other stuff around that was actually working. But I think then just over the last couple of years, there was just so much new developments happening, and I think it's certainly something where you always need to integrate like the latest state of the art, but then also because we have this kind of system system based approach here. It's certainly also a challenge, because we also want to be very flexible, but also like running stuff on mobile phones, having like limited hardware. I mean, I think it's improving over time. And I think it's only a question until like we will be able to just run latest models on there as well, just directly. But yeah, I think it's always like something where you just like you're always a bit behind if you like try to actually develop like a fully working system.
Yep. Okay. Okay. Thank you very much, Professor Stephanie Stillman. So I think we can go to the next talk. Thank you very much. Thank you.
Thank you. Thanks so much for having me.
Thank you. Thank you. Okay. So I will share my screen. Where is my slides? Yep. Okay. So we go to the next talk. So the next speaker is Professor Ziqi Wang from EPFL and Hong University of Science and Technology. Ziqi Wang is a postdoctoral researcher jointly appointed at the Creative Computation Lab and SICAMO at EPFL. Before this, he was a postdoctoral researcher at the Computational Robotics Lab, ETH Zurich, and he completed his PhD at the Geometric Computing Laboratory at EPFL in 2021, guided by Professor Mark Pauli. He received his bachelor's degree in mathematics in 2017 from the University of Science and Technology of China. His research interests focus on geometric modeling, digital fabrication, and robotics assembly. And this fall, Professor Ziqi Wang will join the Hong Kong University of Science and Technology as an assistant professor. He's seeking PhD students interested in digital fabrication and robotic assembly for fall 2025. The title of his talk is Computational Assemblies, Bridging the Gap from the Concept to Production. Okay, so Ziqi, the time is yours.
Thank you very much for the introduction. Let me share my screen. I think this one is okay. Yeah, let me know if it's not. So thank you very much for the introduction again. I actually have the same surname as the hoster. I'm also called I would call Wang, and my first name is Ziqi. And today my talk is mostly about the computational assemblies. Before introducing that, I want to also do a quick introduction of my education background. I actually did mathematics during my bachelor degrees. I'm going to computer graphics because Professor Li Gang Liu, he introduced me to the graphics, and later I started my PhD in a graphics lab at EPFL, where my professor is Mark Pauli. Most of my PhD research is focused on designing architectural structures using geometry modeling methods. Later on, I realized if I can design interesting architecture buildings, can I use robot to build them? That's why I joined the Professor Stelian's Chorus lab at ETH to use robots for building the structure we design. To actually build something interesting, that motivates me to join a true architecture lab, and also with people from controls. So I actually work with Professor Stefana and Professor Mayam to actually apply the knowledge we learned from the past to build structures using robots. I will soon join the UST, the Hong Kong University of Science and Technology, as assistant professor, where we want to develop algorithm for both design and fabricate complex assemblies. So we name our lab the Computational Assemblies Lab. And we are currently looking for PhD students to work with us if if they're interested in either digital fabrication or robotic assemblies, or in general geometry related research. So today I'm going to talk about assemblies, but what exactly is assembly? So we consider assemblies as a joint of parts to make some functionalities. For example, this is a puzzle we designed several years ago. Well, these four pieces parts can be joined together to form a very stable cubes. So assembly can be very small, but also assembly can be very big, massive, and functional. For example, this virtual garden I participate is a leading project by the Grandmaster Color Research from ETH. The specialty of this project is that the structure is modularized, and each modules are assembled using robots. Here, 4 robots are assembled one of the wooden pot by combining wooden plates together. So my role in this project is to helping them to compute the trajectory of these 4 robots to make sure they are not collide with each other. So that's the because of the big spectrum of assemblies that you can go from very, very small toys to very large architecture structures makes me feel interested in this field, and spend several years on researching how to make and how design and making assemblies. I think the current limitation of assemblies is that most of the products or the assembly products are made using mass production techniques. So they are looked very close to each other's. Another big limitation is that the full potential of robots has not been fully exploited. Usually robots are just do a repetitive assembly task, but they can definitely do more. So that's motivates us, or motivates me to do research that can encourage more customization, flexible productions. So the ultimate goal of my research is to allow users to convert their high-level design ideas into a digital model using artificial intelligence. And we use robots to further materialize this digital model into physical products. I believe computer graphics in this pipeline can provide more advanced modeling tools for artificial intelligence part, and also can provide more sophisticated, realistic simulation tools to help robots to understand the environment and be more flexible in terms of fabrication. So the ultimate goal is to create a seamless end-to-end design to production workflow so that everyone can design and fabricate their ideas. So we hope that we can transform the factories from mass production to more customized production or flexible production. In this talk, I will briefly introduce 3 topics of my research. The first one is mostly about the modular design. A big motivation to design in modular is because to achieve customization, the cost of each of the parts play important roles. You cannot 3D printing all of them. For example, in these frame structures, which done by a group from ETH, if you want to achieve this very customized, stylish designs, you need to use a lot of 3D printing joints, which are super expensive. It's okay if you do this for once, but if you want to make it accessible to the general public, the price of the structure is pretty expensive. That's why we think about whether we can use a modulars like Legos to design but still design a customized structure. So in this project, we're using this scaffold clamps and 1 meter long beams as a basic component of our structures. Therefore, there's no labeling or cutting or even unstandard things are needed in this project. And we can connect 2 beams tangentially for making a frame structure. We also got some inspiration from the traditional Chinese architecture, especially the indigenous practice in the Cantonese region, where people use bamboo beams to build a temple or a theater. But they use a wire instead of a scaffold clamps to connect the beams. I think one limitation of the traditional way of building is they don't have a systematic way to design a structure. They usually do by passing knowledge from generation to generation. However, we want to make these things more automatic, more accessible to the people without this specific knowledge. So the main challenge here is that usually the designer propose a design like the left, which is a line graph. Each of the edge in this line graph represents a beams. But the true challenge is how to convert this line graph into a scaffold frames that the bars are connected via the scaffold clamps. So the big difference is at the left, the edge are connected at the end, so they are connected to one vertex. But the left, every 2 pair of beams are connected tangentially. So they follow a different mechanism, how to make this translation automatic. Maybe in 2D it's not so obvious, but in the 3D it's super challenging for designers without experience. As yeah, there are so many ways to do this conversion, but which one are actually feasible? It's a tough question. So therefore, this motivates us to using numerical optimization to make this translation automatic. Therefore, the designers can focus on high-level aspect of their designs, like the aesthetic of the structure, rather than be annoyed by the low-level fabrication details. We consider a few constraints to ensure this translation is valid. First is the tangential constraints. Because beams should connected tangentially, so the distance between the 2 beams should equals to the gap defined by the clamps. They cannot be too far or too close. If they are too close, then the beams may collide to each other, which is also not allowed. We consider this as a collision constraints, and we try to avoid it. Lastly, it's more like structure constraints. It's because if you not pay attention, consider the connectivity of the bars, then some part of the structure may be detached from the original ones, making the final design unstable. So we ensure that if the beams are connected in the line graph, they should also somehow connected in the end in the scaffold designs. We can formulate the whole problem using mixed integer programming, but this is a very challenging problem to solve. It's non-convex. It's binary. It's a mixed integer. So we propose several ways to simplify the solving. But still, the equations are just follow the three constraints we set before. It should be tangential, should be collision free, and should be connected at each joint. The first approach or simplified approach we add into the equation is to introduce a variable called contact variables. Basically, we want to automate the assignment of the clamps. For example, for a 5-beam structure, you can use 4 clamps to connect them. We also can use 8 clamps to connect them. So we consider this as part of the optimization. So we use a variable code called Cij, which means the beam I and beam J should be connected, or should be whether they are connected is defined by these binary variables. But we also realize that this variable is not enough. Actually, the orientation or which one is on the top, which on the bottom is actually also very important. We call this up-down variables. So the dark beams on the left is actually above the white beams, and the on the right is the opposite. So introducing this additional up and down variables actually helping the algorithm to converge. One special thing in this project is the initial design, the line graph, is actually not a good initial point for the optimization, as they are not satisfy the constraints. So, but most of the optimization, especially the interior point method, requires the initial point to be a feasible point. So therefore, we actually introduce an additional variable called the bar radius. So what we discover in this project is that the initial line graph is actually a scaffold structure, but the radius of their bars is 0. So this actually help us to naturally obtain feasible points for our optimization. And what we do is gradually increase the radius of the bars from the line graph all the way to the final structure with the radius of 1 centimeters. I think this is a very good way to ensure that we can use state-of-art optimization algorithms. An additional 2 techniques we use in this project is we find that actually after the optimization, the difference between the optimized variables and the initial variable is not too far away. So we can use sequential linear programming, or basically we approximate each of the constraints using a linear as a linear constraints, which helps to make the optimization run faster, or more robust in some sense. So the whole problem is solving using a sequence or like a list of linear programming with the binary constraints. But because we use a linear approximation, we have to make sure that the approximation error is not too big to broken the constraints. So we use a trust region method to gradually decrease the trust region size until it converges. Because this is actually a project collaborated with architecture students, so we make sure that our tools can be used by them in their most familiar framework. So we develop a plugin in the Grasshopper. This is very widely used software in the digital fabrication or more general 3D architecture domains. So we can allow the user to input their designs directly in this software, and our method can automatically convert this line graph into scaffold designs and send back the data afterwards. So the user don't need to jump into our Python code or very complicated software interface, but rather in working with their familiar environment actually help to increase the productivity. That's what we said. We actually collaborate with architecture students. There are two master students doing for their master thesis at ETH, and they designed two structures using our methods. And both structures actually share the same components. So the first one is it's called arch columns. It's actually a pretty big structure with 6 meters times 6 meters in width, and the height is like 3 meters. So the AR or VR actually help in this project in two aspects. First is that they can visualize the designs directly on the VR to check whether the design is feasible or there's something need to be changed before the production. The VR or the AR also helps the assembly process, as it also show the spatial positions or the orientation of each beams, so the students can follow these instructions to build the structure. We take a modularized way, so the whole structure is like 10 modules. We can assemble the module individually inside the factories, the houses, and then we transport to the final construction site for installation. I think the module installation time, module pre-assemble time is like 24 hours, but the final combination time is just 5 hours. We also do a scan of the structure and to try to see how far the final one is compared with the digital designs. There's still some deviations we discover in this project because of the deformation caused by the timber materials. So the timber is a flexible materials that will deform in the gravity, so we see a little bit deviation at the top. This is also something we want to address in the future. So whether we can actively correct the errors during the fabrication phase. We are not stopped by that because this project is basically to facilitate reuse, to encourage reuse. So we actually reuse all the beams and scaffold to build another structure inside the buildings, which actually is exactly behind my students' master thesis defense to give a impression to their juries. And the structure is similar size, 6 meters times 6 meters in width, and I think takes 18 hours to assemble the modules and another 3 hours for combine the final modules. This is the end of the first one. But most of the structure is still assembled by humans, and we also discovered in this actually will motivate us to go to the second project, because we discovered that during the final module combinations, the assembly is pretty difficult for humans, or pretty unstable during the assembly process, because especially in this large scale assemblies, the structure deforms. And you have to make sure that they are stable, otherwise it's pretty dangerous. So for how to find the optimal construction process, because you cannot assemble them in once, you have to do them in steps. How to find the best assembly steps is a very interesting question and a very practical question. To simplify the problem, we actually consider a more general frame structures like this one. And we ask how to make the assembly more easier for humans or even more easier for robots. The big challenge in the planning assemblies process is that the structure may deform during the assembly process. And if you have a non-optimized structures, the deformation can be huge, which may jeopardize or even or even completely or even cause some catastrophic failures during the construction. That's why we want to first simulate the possible deviations during assembly. So we're using the finite element methods to compute the internal compliance energy of the structure at each of the assembly steps. This energy actually reflects the amount of deformations the structure can have. The higher it is, the higher the deformation becomes. And our goal is to find a design set with or assembly sequence that with minimum compliance energies. But the challenge is that you have so many ways to build the structures, which are the most optimal ways with the lowest compliance energies. For example, if you use classical assembly by disassembly strategies, you still can have a large deformations, especially at the beginning of the sequence. So our algorithm actually allows to quickly generate a sequence with less deformations. I think the big contribution of this work is to actually provide a new perspective of viewing assembly process. So instead of thinking about which part should go first and which part should go next, we actually consider the design variables as all the intermediate assembly states. So the goal of the objective of optimization is actually to minimize the compliance energy of the sum of all the intermediate assembly stage, where we propose additional constraint called temporal coherency constraints, which ensures that the previous assembly state, intermediate assembly state, is included by the next assembly states. Therefore, the parts that are already being started will not be disassembled afterwards. This makes sure that the final assembly sequence is valid or can be done efficiently. And the whole problem likely is to be a convex optimization. Unfortunately, the design variables are binary variables, so there's still a mixed integer or binary convex optimization, but there are some optimization strategies allow us to solve them quickly. Therefore, we can find a good assembly sequence with small deformations in short amount of time using this approach. Like here, we can assemble 4 bars at a time and minimize the compliance energy. We also can introduce additional scaffolds. For example, this arch, we use a three static poles to support the structure. And our goal is to both find the sequence and also the position where the pole should support, or we can allow dynamic spots, which can be achieved using robots, because robots can change their holding positions through steps. Both approach allow us to save like 95% of the compliance energies compared with the sequence without using the spot. We also find that AR can help accelerate or demonstrate or illustrate the assembly sequence. So in this video, my colleagues using HoloLens 2 to visualize this assembly sequence. I think this way is more intuitive because it not only shows which bar should go first, but also shows the orientations the parts should be in the 3D spatials. I don't know whether you have audience have experience assembling IKEA. I think the challenge is not the parts you want to assemble, is actually to orientate the parts, follow the instructions. And this AR actually achieve this easily because they basically show every detail of the parts in the spatials, and you can just follow these highlight virtual models to assemble your structures. So we actually achieve like 2 times the performance, or save 2 times, half of the time in assemblies using AR without using compared without using AR. Of course, we cannot assemble the structure without help from the robots, and we also generate this video Well, we first compute the sequence using our software, then we compute the motion of the robots to sample this arch. Okay, the last part of the project is mostly about the how to, if you finally build a structure, how to make it more robust by optimizing its structural performance. The simple question for this project is if you have a cubes, how to use this to build stable floors. This is a very interesting, also a geometrically interesting problem, also a challenging one, because even you have this floor with the boundary fixed, the structure is still not stable because you can take any of the parts out, assuming you don't have any friction. But if you do some transformation of the cubes, you actually can find good designs that are pretty stable without using any friction or mortar. So if you but you have to assume the boundary fixed. So if you push the parts in any directions, it's still stable. The stability of the structure is because if you take in any of this blue, for example, this blue parts, focus on this blue part, you will see that it's actually locked by its 6 neighbors. So if you move this blue part in any of the directions, it will collide with its neighbor, and this collision will propagate to the boundaries, but at the boundaries fixed, so the structure is stable in the end. So there are several literature that already discussed this long ago to use this kind of mechanism to design stable floors. But our contribution is that we can start from the reference surface, a 3D reference surface. We can use the 3D conformal mapping and some kind of geometry optimization to create a 3D assemblies. And this assembly is actually named the topological interlocking assemblies because they are actually stable because of their topological arrangement. So the key approach we discovered in this project is that the interlocking cube is actually oriented in a special way. Why they are oriented in this way is because compared with a regular cube, both of them actually share the same hexagonal cross sections, but for the regular cube, the cross section is actually oriented diagonally, and in the interlocking cube, the hexagonal actually oriented upwards. So if you can transform the regular cube, the orientation of the regular cube following to the upward direction, you will get the interlocking cube. But for this and you can actually making these whole floors by first tiling hexagonal patterns, and then put each of the interlocking cube on these hexagonal patterns to create the floor designs. First, for 3D, this will be more challenging, but still you can do this by first tessellate the input surface using hexagonal patterns. Then you assign each of the hexagonal edges with vectors represent the faces of each of the blocks. By varying these edges, you can get a different topological interlocking structures. This can be visualized by using these animations, so we can increase the angle of these vectors to create a series of topological interlocking assemblies. But the question is whether the stability that we have seen in the 2D also apply in the 3D, whether this DOM is stable or not. This is not a straightforward question because, or it's not a binary question because some structure actually is not stable in the gravity if you flip them, because they can move in different directions simultaneously, which actually causes the structure to fall down. That's why we developed some algorithm to actually first analyze which structure is stable and also design structure that actually can be stable. So for example, this minimal surface we discovered is actually also have the same properties as their 2D counterpart. that you can actually rotate them, flip them without causing any problem. But if you destroy the integrity of the boundary, the structure can collapse, which also indicates that we don't use any mortar glue. We also find a structure that actually can be tilted to certain degrees, like 30 degrees, until it falls. So we also can optimize this ability of being tilted, which actually useful whether to bear the force from the lateral side. But what happens if the design is not stable? So we also have some algorithm that can automatically convert or find the best interface or optimized interface to make the structure stable. So this part is called inverse design, and which is done by using bilateral optimization. So the internal part of the optimization is to compute the stability how far the structure becomes stable, and we actually minimize this measurement to find good designs. The whole optimization is solved using sensitive analyze, basically compute the derivative and hashing of the optimization, and using Newton method to find the optimal to find the stable designs. And this is a video of this approach in 3D, so we can also optimize the stabilities in the tilting stabilities. So we want the structure to be able to tilt more by using the bilateral optimization we just showed before. This project also inspires some following research, collaborate with mechanical engineering, so we can actually assemble the structure automatically using basically the ship memory alloy. We plan some ship memory alloy inside the parts, and when we give some electricities, the ship memory alloy will shrink, which actually trigger this self-assembly mechanism. So because our structure is stable when they assemble, so it can actually bear some loads, and you can also have different shapes using this self-assembly mechanisms. Okay, that's the end of the presentation. To go do a quick conclusions. In the first project, our goal is to reduce the material costs using modular designs. And the second project, we are more interested in how to make the fabrication cost low using robotic assemblies. And in last, we actually enhance the stability of the structures using some optimization. Maybe some quick discuss of the future work. One project we do now is actually how to do a human-robot collaborations. Like the human can design a small SketchUp models at the left, and robots can help them to realize their SketchUp models on the right to make this translation automatic. Another project we are also working with is like a human-robot collaborative assemblies. It's basically human can assemble some difficult parts in structures, but the robots can do more heavy lifting in a project. And this is actually been done recently. So the robots can hold the big beams to support the structure, and human can assemble the small beams to finish up. And the modules are assembled in the factories, but they are actually installed it using helicopters in a mountains region for illustrations. This actually motivates us to also further go this direction, thinking whether we can use drones to replace the helicopters, and maybe in the future we can use drones to help this this difficult terrain constructions. That's it. Thank you very much.
Thank you for that, Professor Ziqiwang. So I will ask a question. So in your work, are the shapes of the modular parts are predefined or post-computed? Any pros or cons for the two design approaches, the predefined parts or the parts from optimization?
So we currently fix the modules. It's like Legos. You cannot have your own Lego set. You need to use from inventory that the market already provides. So we didn't design the module parts. But the structure the final structure can be general, more flexible. You can do whatever but you have to use this special components. And our future research actually is to also think about how to design modules so you can reduce maybe you can use a 10 set or like a 50 set, but you can cover all furnitures in your home, for example. You can use this 50 or 10, 10 or 50 parts, but you can use them to build the chairs, tables, all of them. And how to find both optimal module components and also the how to ensure that you can enough flexibility in terms of the final structure is an interesting problem we want to achieve.
Mhm.
Uh,
Okay.
Yeah.
So the next question is you mentioned that your goal is to bridge AI and graphics. So is there any possibility to leverage AI, for example, to LLM to design physical plausible assemblies?
Yes. So that's something we also want to do. If you're interested, if any in the audience want to be a PhD in this field, I'm very interested to work with you. I think the challenging for compare with the current AIGC, like the or the text to 3D or image to 3D problem is we need a model to be fabricated in the end. So that's the main difference. So we cannot have a noisy mesh or even like I think except using 3D printing, a majority of the current text to 3D software, the mesh they generate is not good enough for fabrication. So one approach we are thinking maybe is to using a code generation, because most of the CAD model or the model that can be fabricated in the manufacturing is actually it's kind of a code. So it's like a CAD code. There's a software called OpenSCAD. So you can use a code to generate the designs, which are more structured, more clean, more easy to use, and more parameterized. So maybe there's some approach we can do in this field is to combine with LLM, the code generation abilities, and also some reinforcement learning methods that you can explore um, the code generations using reinforcement learning, and you can easily have some reward to encourage the agent to learn how to create a functional 3D models, because the challenge here is also the data is very sparse. There are not too much data as you can have, so maybe the reinforcement learning can definitely help you. And the LLM can actually be basically a regularization, or like the code they generate is more meaningful. So the IO agent do not need to learn this part. Like they only need to focus on how to make a good models in a very low dimensional space.
Mhm. Thank you. So at the end of your talk, you talked about the human-robot collaborative construction. So my question is there, any possible or designed the task divisions for the human and for the robots? So what job do the robots do, and what job do the human do?
Yes.
So are there any, yes. Mhm.
Yeah, this is a very good question. So it's also I think in general the I think the how to use robots uh, in a good way, it's a tough question, because you either do fully automatic, or you do fully manually. Like something in between, it's a very hard question to argue. Like, but we realize that especially in constructions, robots actually more good at heavy duty stuff like lifting a super heavy beams. Maybe you need this because the structure is unstable at the moment. You have to have someone to hold for you, and human is very hard to do this because it's very tough job, and you cannot do for long. Like you can do 5 minutes, but after an hour, it's a pain. That's why robots can the current state of the robots can do this, and human can do more tasks that requires a very delicacy or like a very detailed operations, like especially manipulation tasks like screws or like nails. Robots can do it, but they need a very good first vision system, and also very advanced software to achieve this, but humans can do this in 5 seconds. That's of course through the development of robotics, the task robot can do will be widened and wider. So that's something we also interested. But I think that at the moment this is actually a good allocation of the task.
Mhm. Thank you very much. Thank you, Ziqi. So any students who are interested to the thesis work, please talk to him. He's, finding potential PhD students. Thank you, Professor Ziqi Wang. So
Thank
I
you.
think this concludes our webinar today. Thank you very much for the audience. Thank you, Professor Ziqi. See you next time. Bye bye.
Bye bye.
Bye bye.